Hi everyone. Uh, Welcome to the session on the quantum computing fundamentals, QCF 101, session 5. And here we go. We start with the uh, part 1, and this time we will cover part 1, part 2 together, as Professor Gokhale is not present. But however, I am shortening what 5 will contain. So as per the timetable, we have June, July, August, and September. We are in the June 26th. So this will be our fifth session. One more session we need to complete. We'll complete it probably in July first week. Uh, so the fundamental, we have around 12 chapters. We are covering, this will be covering 9th and 10th of the prescribed book, which is here, Introduction to Quantum Computing. So the coverage will include eigenvalues and matrix diagonalization, unitary matrix, unitary transformation, construction of unitary transformation matrices, completeness of the basis, uh, construct the operator given the eigenvalue and the eigenvectors, and we'll go into problem assignments and what we do in the next class. So recapping what we did previously, I will say that you can think of matrix in your machine is as your machine. So if matrix is your machine, then it's the one which operates, and so you do the operation. So matrix is in turn is your operator. And what does the operator do? The machine is there and you throw a vector at it, it will crank it and put out a new vector. So basically machine equal to operator equal to matrix, and it's crunching some vector and producing some vector. It's not arbitrary vector, we need to have some specific vector. So what we are talking about is we need to be, so there is something in quantum computing called observables. So if there is an observable, uh, then if you can measure associated with that observation in the vector space, like if time t equal to 0 or time t1, etc., you are observing and you are able to measure the output vector in the vector space, and that's what is desirable. Now, a vector, when we said, we previously defined, we can measure direct measurement through position of a vector, like position vector of a particle, example spin. It could be at the xyz origin, or it could be from xyz to a length which is in millimeter, so maybe unit vector. So a vector which is unit length from the origin, that's the position vector. And if that vector we can measure, that is the observable, and that is the equivalent of measurement if we are able to get some uh, tangible numbers which we can, example 1 millimeter, right? Same way we can talk about a momentum of a particle like wave, and we say, oh, okay, it has got a 1 joule or 1 joule per hertz as some uh, measurable thing associated with the observation. Or we can talk of angular momentum of system like r omega r delta theta by delta t, which is nothing but rotational momentum or angular momentum. So these are physical, right? So we are trying to get the physical meaning of what the rotation, the machine which cranks the vector into another vector, turns out to be. And the observables themselves are not state vectors. Uh, the, they are the things you measure. Like if I say sigma x, sigma y, sigma z, we spoke about some matrices. Those are the ones uh, you measure, and we call them as linear operators. Why linear operator? Because all operators are not linear. There can be non-linear operator, but Linear operator is that it will always produce a linear output, and that output is interpretable in terms of what we call eigenvalues as plus minus one example, and which is what the quantum does. You can have any eigenvalue. You can have values eigenvalues which are in matrix terms. They can be 3, 5, 2, or any complex number, but that doesn't count. We are restricting in quantum to a value which is scalar. And so we say if we have a matrix M or a machine M, we call it, and if you are having a vector V1, and if you can produce by cranking that matrix or the machine to produce another vector V2, which is a multiple complex scalar of vector V1, then we call it as a ZV2. So that means we cranked a machine or a matrix on a vector V1 and produced a scalar vector, complex scalar vector ZV2, which is what we are looking for. And there are many other restrictions, like we said, it should be a linear operator, so machine should be not be non-linear, it should be linear. It should convert to scale so that we can measure it, and that's the goal behind the computational aspects of matrix operator and machine, whatever we call it. So let's get into the detail. We are focused right now on eigenvalues and matrix diagonalization. So if we say lambda I, in this case you say lambda I, okay, is a, it's a notation, abstract notation. So let's say if lambda I is a scalar, that means what? It is some complex number or real number, whatever. So it's a scalar. So if we say that if you have matrix A, which we call as operator, is operating on a vector, and this case we call it as I vector, it can be anything. We say abstract AI. So a matrix A operating on ket I, which is the representation of vector in ket notation, is equal to lambda I of ket I. Essentially, what we are trying to target is that if I get a vector I and if I operate a matrix on this vector, we are getting a scalar lambda I times the vector, so which is nothing lambda I. So our goal is to obtain a lambda I which is scalar, and that lambda I can have a scalar value, then only it's a linear combination of vectors. So in other words, let's say if lambda I is, now how many uh, vector states we have? It's a combination, right? Linear combination. So A0, 0 plus A0, A0, 0 alpha, lambda 1, lambda 0 plus A0, 1, lambda 1 to A0, n minus 1, lambda uh, n. And same way we can go with others, and ultimately we'll have last matrix row, which will be an minus 1 alpha n, an minus 1 0 alpha, what do you call, alpha n minus 1 up to an minus 1 n minus 1 alpha n minus 1. So basically matrix A can be represented by aij, where I and j can go from 0 to n minus 1, and similarly we can represent the vector I as a column matrix alpha 0 coefficients to alpha n minus 1 coefficient. That's the presentation there. So if I say A into vector I, that means what? I am trying to take a matrix with a coefficient of A0 to A00 to an minus 1 n minus 1 and multiplying by a column vector which is representative of the column vector, because there are, and in the case of ket0 we said it is a 1 0. In the case of ket1 we called it 0 1 because there are only two. But if there are n, then what happens? Then it will be a column matrix alpha 0 to alpha n minus 1, and which is equal to lambda I into this. So what is this lambda I representation of? We talked about diagonalization. So if you have vector, if you have a matrix and that matrix diagonal is all 1, then we call it as ID matrix and rest of them are 0. So that is a identity matrix. In this case, what we are saying that we are trying to get the lambda I as the elements of the diagonal vector, so that when you multiply with a column vector, you are getting combination of alpha 0, lambda 0, alpha 1, lambda alpha n minus 1, lambda n minus 1. So basically, first thing we said is, if you take a matrix and crank on a let it apply to a vector of I, in this case I can be 0 to n minus 1, that is what, it's a column vector of n minus n elements, and so there will be a lambda I, which is nothing but again lambda will be 0 to n minus 1, so basically n lambdas. So diagonally n lambdas, which will, if we multiply and all the rest of them are 0, then that's what means that lambda will be scalar. So we can look at it in this way. So if I go and get into, in general, we represent a matrix using its eigenvectors as basis vectors. So these are the eigenvectors. Okay, and then eigenvalues are the diagonal elements. So we have diagonalized the eigenvalues and columnized for a ket space, which is, in this case we are talking about ket I, and I is the identity. So basically what we have done, A into ket I is equal to lambda I into identity matrix into I. Simple. I, if you multiply I identity matrix, it is like a number 1. Anything multiplied with number 1 remains the same. So that's the beauty of it. So lambda I ket I is equal to lambda I into ket I, where I is the identity matrix. So if we move this left side to right side, then we'll have A minus lambda I, because I is common both sides, we have bracket taken out. So AI minus lambda I into ket I. So if we do that, and that means we can equate it to 0 to identify, and 0 equivalent is column matrix 0 here we have taken, because it's the vector we are looking for is in the column matrix space. So which is n by 1, n row by 1 column. So now the trivial, if you have a trivial answer, the trivial answer is what? A, your vector itself is 0, forget it, then there is nothing solution. But if we say no, we don't accept that, then the lambda I must have some value. So what is that value? So our goal is to find out if A is equal to lambda I, then, because A minus, either this is 0 or this is 0. If this is not 0, this is 0. If this is 0, then A equal to lambda I, that's what into I. And so we are looking for that solution, and that solution will turn out to be what? That solution will turn out to be that we will get some vector which is nothing but minus lambda I for a 2. Let's say this is generic, and if we take for a 2 dimension, then we are going to get A00 minus lambda A01, A10, A11 minus lambda I, which is nothing but, if we say that if we are going to take this determinant, which is a determinant. So basically we are saying determinant is 0. If the determinant A minus lambda I is 0, then what we are getting is minus lambda I minus lambda I 1, 1. So basically it is turning out that lambda I square minus 1, 1, 0. Therefore the lambda I square equal to 1. That's what we are getting at the end of it. So lambda I is equal to plus minus 1. Lambda 0, lambda 1, lambda. So either we say lambda I is plus minus 1, or we can assign lambda 0 equal to 1 and lambda 1 equal to 1, which is fair, because at the end of it lambda is plus or minus 1. So if you have 2, then we say lambda 0 is 1 and lambda 1 is minus 1. Now if you substitute this and try to solve the problem, then you will find that you can do it on, this is based on what? The question is, this is based on to find an eigenvalue, eigenvector sigma x, since we are referring to 0, 1, 1, 0, a sigma x vector, when we solve for a sigma x, then the sigma x will turn out to be a 1 by root 2 of column 1, 1, and so lambda 0 is equal to 1, and then we are getting a, there is eigenvalue is a 1, and the eigenvector is nothing but 1 by root 2 column 1, 1, and lambda 0 is my eigenvector is 1 by root 2 column 1 minus 1. Now this is computed on the basis for sigma x, and we have to be very careful because we wanted that our eigenvalues to be minus 1 plus 1 or plus minus 1, and the basis of computation for is z. If we use z, then that is what will be normal default. But since we have here a sigma x, it is going to be not a 1 0 but a 1 by root 2. So basically it is not unitary, or it is not unit vector, because we chose to solve for sigma x. Now here we have to be cautious because we do have many possible way to measure for 2 by 2 matrix. As we said, the only condition we are restricting our eigenvalues to be plus minus 1. Eigenvector, whatever it turns out, we are not very particular about eigenvector, but we are particular about eigenvalue. As long as we get plus minus 1 as eigenvalue, whatever it turns out, we can always normalize provided we have measured on the basis of z, which is the normal default we take. That means if we are measuring with respect to sigma z, then only we can accept it. The calculations are here. We can I can show you just to get you some what you call the presentation which I have shared, so that you are able to calculate eigenvalues, because eigenvalues are not restricted to, eigenvalues can be any number in matrix calculation, but for quantum purposes we are restricting it to plus minus 1. So neither it is scaling to plus 2 minus 2 or 1 by root 2 or 1 by root 2, or is it squeezing. So neither it is squeezing nor scaling, it is maintaining unity, and that is what the eigenvalues and eigenvectors we will like to have for our observable measurements. So E values or eigenvalues will be plus minus 1 for all our purposes. How we achieve that? That depends on what matrix you use. So our options are matrix option. The other option is the vector option. So what matrix, what matrix on what vector we operate, and that enables us to produce plus minus 1 so that they are measurable. That is a good. It's not like you cannot have uh, uh, values non ones, that is not plus minus 1, but they are not measurable, then we'll have to normalize. So we are looking at quantum in terms of plus minus 1 as the eigenvalue. The only thing you remember is plus minus 1 eigenvalue is the requirement. Matrix can change, vector can change, because you have to operate on all vectors that are available in a unity sphere in the given quantum vector space. So that's the summary of what we have for previous work what we have done. Now I will go to uh, unitary matrix. Okay, last time we covered Hermitian matrix, which was uh, Hermitian was, that is, if you have a adjoint of a matrix, uh, that is, so unitary matrix we are defining as whose adjoint U dagger equals to inverse. Hermitian, what we had seen, if you have a vector or if you have a matrix, and if you find the adjacent that is the adjoint matrix, self-adjoint we call it. So if you have a matrix and self-adjoint is equal to matrix itself, then we called it as Hermitian matrix. So here instead of itself, matrix itself is its Hermitian. Instead of that, we are saying a unitary matrix is defined as a matrix whose adjoint is a conjugate complex of the matrix. And so that means this is little different. Here we are saying if U dagger, if you have a matrix U and you are taking a U dagger, which is nothing, the complex conjugate transpose. If that is equal to whatever matrix U2 raised to -1, that means it is inverse of it. So we are talking of unitary matrix as being complex conjugate of the matrix being equal to inverse of it. Or alternately, you can say that complex conjugate of a U multiplied by unit itself is equal to identity matrix, because if you take U to the other side, uh, that's where you can see that either you take a U dagger U or U dagger which are in the what you call adjacency space or adjoint space, then E is equal to identity matrix. So by definition, unitary matrix is a matrix whose complex conjugate is equal to inverse of the matrix. So the matrix U is 1. If its inverse is equal to complex conjugate, vice versa, either way, or multiply both of them, you will end up in an identity matrix. That is the so if you have two vectors, say uh, F and G, so if you take the unitary matrix and operate on F and you operate on G, then what happens? You should multiply UF with UG. So you are taking two unitary matrix, one you are applying on F, one you are applying on G, same unitary matrix. Now what happens? In the complex conjugate, in the Ket space, if we take a UF, it can be represented as bra F with a U dagger, which is what, because you are converting a Ket space to a matrix in the vector in the adjoint space. So that means in the bra space. So Ket F becomes bra F, U becomes U dagger, and then since we are multiplying the two vectors UG, UG remains UG. We have not done anything to it. So the multiplication of these two leads to bra F, U dagger. We have said it's nothing but identity matrix. So I into G. So I is, you can drop the I and just keep it as FG. So what it means is, if you have a unitary matrix and you have two vectors, if you take a dot product of the two, that is preserved. Essentially, inner product is conserved if the rotation matrix is unitary. So we are talking about an operator. Unitary matrix is the operator. The quality of, or the characteristics of unitary matrix is that it will preserve when two vectors multiply, product of two vectors, it will always preserve the uh, dot products, which is scalar, right? Which is what we are interested in. So that is the unitary matrix. Now you can look at unitary matrix. Uh, how do we show it? Like how do we make it for a n dimension? So if it is an n dimension, then you have got, let's say, here is the matrix B0 to Bn minus 1 with a Bn 2. So this is the n by n matrix 0 to n minus 1, which is a B matrix. So if this is the matrix, which is U, if we take a complex conjugate of it, it will have all its corresponding coefficients as conjugate complex. Obviously, so we are making everything conjugate complex. And if you do a multiplication of this will give you identity matrix that we have already defined per definition. So essentially, this is nothing. It's the inner product of the ith row of the vector of U dagger and jth column of vector U. So that means if I say this is 0, 1, then this is 0, 1. So basically, ith row with jth column multiplication. That's what it ends up. That's how you are getting all this uh, identity. So basically what we can rewrite, these are the general terms expressing the same thing. But if we take a Vi and a Vj, if you do a dot product of the two vectors Vi and Vj, it is equal to this is the delta Ij, this Kronecker, which is if you want to express I equal to j, what happens? If you say I is not equal to j, what happens? So I equal to j, everything will be 1. I not equal to j, everything will be 0. That's what it means. So canonical delta test inner product are 0 if they are not from the same columns, and 1 if they are from the same column. So if they are in this, so if I say Ij is equal to I, so there I equal to j is this diagonal, and if they are in diagonal, all are unity. If they are not, then all are 0. Obviously, this is the fundamental which we have studied of what you call orthogonal normality, which is if it is orthogonal and normal, then their product you will not have any common thing between them, and they will be 0, right? So except so this is the standard unitary matrix. So the only thing we remember on this is if you have a unitary matrix, the complex conjugate transport of it is equal to inverse of the matrix, or the other way around is u dagger u equal to identity matrix is equal to u dagger. You can see both way it is same, because these Ket-Brahe spaces are complex conjugate in themselves. If you say you take a complex conjugate, you get u dagger. If you take a u dagger and take a complex conjugate, you get u. So obviously u dagger, u, they mean the same thing. It's identity matrix, or you can define it as unitary matrix as a inverse. So this is important to note, and let me move on to transformation. So now what happens? Looks and feels of transformation is important. So when we perform coordinate basis transformation, so we have studied the coordinate, XYZ coordinate and all that, right? So if we look at coordinate basis transformation, which is the default transformation of unitary transformation, whatever we call, this is always anti-clockwise. So that means if I have a vector v as shown here, if I move that vector to next location, call it v prime, then the angle theta between them is what counts. And essentially it turns out that if it is unity and if you are transforming to another vector, then the original vector, if it is a linear combination of alpha beta coefficient with k0 k1, then v prime will accordingly be a combination of thereof. And for us, the important thing is it is moved clockwise, but the value has not changed. That means anti-clockwise. We had moved it anti-clockwise. So coordinate basis transformation is it is a anti-clockwise movement. So imagine you watch from a platform, a train is moving, and it appears it is shifting its coordinate, moving ahead. So that is the coordinate basis. Or likewise, you can move your lamp or a notebook on your uh, table. So if you move it from one place to another, doesn't mean the table's shape is going to change. If your table is square or rectangle, it will remain as is, right? The only thing that is moving is the notebook or the lamp which you have on the table. So that is the default anti-clockwise direction is what is depicted for spin-up. Okay. Now, if you talk of another perspective, why should I move the lamp and the notebook? I'm going to move the table. Okay, but to get the same, achieve the same result, what you'll have to do is, if you have moved it clockwise previously, you have to move the table anti-clockwise to get the table or the notebook in front of you with the proper lamp. So what it means is, This is similar to if your train is moving and you are not the passenger in the train, you are outside the train, and then you are looking in. So, uh, so for the passenger who is inside, it will be a different view. Whereas the one who is a, if you are a passenger and you are looking at it, for you it will look platform is moving, right? That's the way. So basically, it's a perception. The one thing which we want to stress here is unitary transformation looks and feels basis on the space is clockwise, anti-clockwise. So anti-clockwise is the norm which we use most often called coordinate basis transformation. But if you are going to take multiple vectors are there, n vectors are there, and they are one to another, and you rather than moving the vectors, you want to move the platform to view it, unitary transformation can be platform basis also. So the transformation of matrix is to rotate a vector by theta anticlockwise or rotate the basis itself. In this case, you can see here the basis is 1 0. Okay, now you are going this way. Instead of that, you're if you start moving the basis itself, which is like moving the table, then you are moving at 0 1 0 prime 1 prime, which is the table position. That means you have moved the platform, right, or the basis. So you can rotate on the vector basis or you can rotate the basis itself. So what it means, the frame of the basis itself you are moving, like your 1 to 1 prime. So it is reverse way. Important point to note. Let's move on. So unitary transformation can be computed in terms of ket, as we said, if we have a vector v alpha 0 plus beta 1 ket 1 alpha ket 0 plus beta ket 1, which is nothing but a, in terms of column matrix, it is alpha beta. So this can also be expressed in terms of trigonometry because we are taking projection in that case. So the projections, if we take of unitary matrix, uh, the computations come out as cos projection and sine projection, and so ket 0 comes out as a cos 0 in the new basis and sine 0, and ket 1 comes as uh, minus sine ket 0 prime cos theta ket prime. So basically they are same thing, but we are expressing trigonometric terms, and they are being expressed as cos theta sine theta minus sine theta cos theta. So this is a projection which we go from a ket 0 ket 1 basis to a ket 0 ket 1, and we saw that in the previous how the basis is itself moved, right? So essentially we are saying if basis is moved, this is what we expect. Now this can be also looked upon as a combination. Example, in this case we have alpha beta for ket 0 as cos theta sin theta, and for ket 1, which is the spin up spin down is minus sin theta, because why that minus is very clear, because this is going down, right? So you are going down, or and if it was clockwise, then it will be plus. So this is plus, but this is minus. So therefore the term minus comes in here. And when you do a unitary matrix multiplication with the unitary matrix which is defined here as cos theta minus sin theta cos theta, you can take this u and take a conjugate uh, conjugate complex conjugate and transpose, which is nothing but you are just taking minus sin theta and cos theta sin theta cos theta. So what it means is you are just taking a uh, uh, complex conjugate transpose of it, which is shown here. So if you take a complex conjugate of the same u dagger, it turns out that your minus sin theta goes transposes out there, and sin a01 a10 reverse change, cos theta remains as is. So the combination of these two, when you do a multiplication row by column cos square theta plus sin theta cos theta minus. Similarly, this one, if you take on this one, you will have minus sin square theta, which is nothing but plus sin square theta, and then minus sin cos. So minus sin cos will cancel, and you will have only uh, sin square theta and cos square theta. So sin square theta plus cos square theta on both terms will turn out to be 1 whereas minus cos sin will end up in 0. So this is equal to 1001, which is limited. So even without even going into this, we can go reverse way also, saying if I have 0 1001, this is equal to identity, then what values should I have cos theta sin theta terms? You can go other way also. Ultimately, at the end of the day, why are we doing this? The bottom line here is, if we are going to change the basis, because when we say unitary transformation, if you go traditional way, that is coordinate way, then you take the vector and then multiply and see the angle and then project it. But if you are going to move the entire frame, unitary transformation, that is the orthogonal, like moving the bench, right? If you are going to do that, then you have to do a clockwise, and that means if you do clockwise rotation, so you have a z x as the surface, and on this zx surface, if you are going to go in a way whereby you are trying to go clockwise, then you are moving that axis, right? X and z, you are tilting, and that tilting, if you do, then you are able to get it on the basis of, instead of doing on a 0 1 basis, which is what is the original formulation, and if you want to do that on a prime, that is 0 prime and 1 prime basis, uh, then you get this formulation, and that is, so it will be coming out as alpha cos theta minus beta sin theta. As you can see, this is just a multiplication. I don't want to get into complicated. Simply, you are moving the basis from 0 1 to ket 0 ket 0 1, which we saw here. This is a fake. Actually, it is not correct, but even in the fake diagram, just to see, perceive it, this is what it is shown, because you are just moving this orthogonal basis 1 0 to basis changes to 1 prime 0 prime, and when you do 1 prime 0 prime, there is an angle between them, and that angle is what matters, and that angle has a theta, and so projection of cos theta you can see, and projection of sin theta, that is what is being used to compute, and at the end of it, when the basis is changed, you are getting this new formula, which is alpha cos theta minus beta sin theta alpha sin theta plus beta cos theta. This is a column vector. This is all one term. Okay, one term. So instead of alpha beta, you are getting this term, and this is alpha cos theta. So basically, earlier we had this, now we have this, and that is the ket 0 prime and ket 1 basis. So unitary transformation can be projected in terms of change, basis change also. That's the uh, sense you can make out of that as a unitary transformation. Coordinate transformation we have already done, we have calculated several times. So I'll leave it that. Now let's do the construction of unitary transformation. How do we construct a unitary? So, okay, here we got it because we took some fake numbers, right? Some angle, and then perceived it, and then actually calculated based on some theta. Now here, how do you construct transformation of a matrix? That means, how do you do the unitary transformation matrix? So we can use trigonometry as if we did in 2D, 3D, like we did earlier. How do we do that in a higher dimension? So the question is, if I have n dimension, then what will I do? Okay, so what we do is, we just first say what are the base vectors. So ket 0, ket 1, ket -1. So it could be ket 0, ket 1, ket 2, ket 3, ket 4, ket 5, ket n minus 1. I am putting in decimal because it doesn't lose any generality. You can put binary, or you can put 0 0 0 1 1 0 1 1 if it is like ket 2, but that we saw last time also. But essentially, I'm just saying ket 0, ket 1, ket 2, ket n minus 1. So if this is the 0 to n minus 1 new basis for n dimensional space, then the matrix corresponding to that will be how? So we know that unitary matrix preserves the dot product. And when you do dot product with any changed basis, it will maintain for that basis. So essentially, whatever the basis change you do, you can do a dot product of that, which is in this case, if we are moving from, we saw previously we moved from original was ket 0, ket 1, we moved to new basis, which is ket 0 and ket 1. And so we are just taking, assuming that we are uh, transforming that for every space. So the coefficients, every coefficient will be a dot product, and that dot will be sustained. So what it means is that if I have two of them, it will be preserved. If it is three of them, it will be preserved. If it's four of them, 4 by 4, n by n. So basically, n by n matrix with a uh, corresponding vector being orthonormal, you will be able to do n minus 1 ket 0, n minus 1 prime ket 1. So this is nothing but if I have say 4, then this will be 4 minus 1, 3. If I have a 0 to n is equal to let's say 4, then we'll have 3 as the last, right? 0, 1, 2, 3. So that means ket 3 bra 0 plus bra 3 ket 0 dot product. Similarly, dot bra 3 ket 1, and last one will be bra 3 ket 3. So basically, you are just taking that particular dimension, and that dimensions an ij vector which you say. So the ith row and jth column element is just the inner product. So whatever I and j we take, that is the row and the column, that basis vector should be within that particular space, because we say when we say x and z as one surface, so within that we are moving xy dimension. So if I have something like y and x, then I should move in y and x. If I have say n minus 1 and n, then I should move. So you can think of n number of surfaces, because each one combination of them should turn out to be a separate space. So n dimension, that is why it is hard to comprehend, but given that we can do it for 2D, 3D, it can be done for m and subspace. So basically, if I have 3D, I can see 2. If I have 2, I can see line. So essentially, if I say 4, then I should be able to see 3 dimensions. If I have 5, I don't know how to visualize 4 dimensions. So this is where the challenge is, and that's why this matrix notation will. All it means is dot products of those in that space should be scalar. Okay, so this is the unitary matrix, and we can calculate that. For example, if I have a sigma z, which is a eigen, we know the sigma z, which is a one which you have been using as a standard basis, right? So the vectors are 1 0, column vector 1 0 and row vector 0 1 for ket 0 and ket 1. So if I take eigenvectors of sigma x, we know that all sigma x, sigma y, sigma z, all of them have to have a eigenvalue of plus minus 1, and that we have computation, we can go through that. But essentially what we are saying is, if we have an eigenvector r plus 1 and minus 1, which are nothing, 1 by root 2, basically probability is half half. 1 by root 2 square is 1 by 2, so half of probability cannot be more than 1. So the probabilities, based on that itself, you can see that quantum state represented by ket 0, ket 1 basis, it is transformation of matrix that represents plus and minus basis. So you are changing the basis, right? You are trying to say xz surface, we are transforming. So that means what? If unitary matrix is a scalar multiplication of the spaces, that is the basis. In this case, we are moving from 0, 0, 1, 1 to minus plus minus plus, right? So that's why Kate minus 0 unitary is this, and therefore if you do the computation on this minus and 0 based on the 50% the probability 1 by 2 1 by 2 and the square, that is a square plus b square equal to 1, or you can say alpha plus square plus beta square is 1, that basis. So you are going to get a scalar multiplication of all of this, and when you compute at the end of it, it comes out to 1 by root 2 minus 1 by root 2 1 by root 2 1 by root 2. So unitary matrix turns out to be this, and this is nothing but the a proof. It's called what do you call? Uh, uh, you can extrapolate basically. So if it is true for 2, for 3 it will be true, and so on and so forth. And that might turn out to be uh, maybe whatever the values turn out, but our eigenvalues and eigenvalues should be plus minus 1. That is the key. Vector can be, so the vector can be um, plus minus, minus I, 0 I. We don't have to worry. As long as it gives a eigenvalue minus 1, 1. That's how good. That's the lambda I definition which you did earlier. So we have to worry about now the completeness. What is completeness here? So when you talk about 0, 1, minus 1, plus 1 as the different basis for every basis in a given dimension. If it is 2-dimension, xz as our surface, then we covered that 0, 1, plus minus 1, all four should be covered for completeness, so that we are able to get uh, correct value. So if it is n dimension, then what happens? So in that case, it is hard to express. So we resort to our Dirac notation, and then space vector, uh, and then for each of this, there are two ways to formulate. One we have seen, one is based on the orthonormal basis of vector space. The another is based on the projection vector, which we had covered last time. So there are two ways to ensure that the completeness is there. And one of the, for this n dimension space, for a vector v, we can represent as linear combination based on the basis vectors I, ket I, where I runs from 0 to n minus 1, which is equal to, that case we said 0 to 1, 2, 3, and up to n minus 1. So if we take that, then uh, assuming that there is a j and a I, two vectors, so j at row and I column, as we said, if you go by that, if we have a vector v that can be represented with a n by n dimension with a I and j, where if I is the one which is 0 to n minus 1, in that case, that is the basis. Then if there is a j which is not I, assume right now it can be I also, but if it is not I, then j into v, all those matrix in that, if not equal to, will become 0. The only valid value will be only the diagonal, because we know diagonalization happens here. So at the end of it, we can represent as 0 to n minus 1 of sigma I using the Kronecker notation ji, which is nothing but saying that if I and j are equal, then only you are going to get any value out of it, and that is the value which is your uh, your scalar. Now this can also be done through projection matrix, as we saw earlier. Projection is you project on the dimension which you are basis dimension. So, but in that case, we, instead of using a what you call the scalar product, we took a determinant, and therefore the determinant, when you take, you do a cross product. So cross product of j with j of a vector v, and that is represented again I equal to 0 to n minus 1 of the jj with vector I. So basically this is the similar thing, but with a probability or projections. When you do projection, that is the projection on the coordinates on the basis of axis, how many axes you have. In this case, if you have 2, we know it turns out to be simpler, but this is the same thing. Essentially, we want to cover that probability doesn't fall short of the projection. That means if you take a projection, then you are taking the value and the sum of those squares of the all the components subspaces should be equal to 1. Otherwise, it is not meeting our requirement of a operator which we are dealing in the Hermitian or unitary space. So at this time, I will say that the completeness is ensured by making sure that we go whole 9 yards from 0 to n minus 1 for n dimension. And extrapolation we have done from 2 dimension to 3 dimension to n dimension. Let me go to the, we can also go reverse way. That is, we previous classes we did, previous sessions what we did, sigma x, sigma z we took and we evaluated the, that is eigenvalue and the eval and e vector, that is eigen value and eigenvector we found for sigma x, sigma z, etc. Given the matrix ket0 equal to column 1 0 and ket1 equal to column 0 1, eigenvalues we got as plus minus 1. Now, if we are given that this is what you have, what is the matrix? Previously, what we did, we took the sigma x, sigma z and tried to find what is the eigenvector and eigenvalue. But now we are given that this is the vector and this is the eigenvalue. What is the matrix? So it is like a reverse operation now. So we'll again go back to same thing, a equal to I equal to 0 to n minus 1 lambda I. In this case, we are taking the products, okay, which is ket I and bra I. So basically, I bra and ket bra into I bra, and that is equivalent to the dot product, the determinant. So here we have, we want to get say z. For z, what we need? We need to have I to 0, z, x, y, z. So we have 0 to 0, 1, that is 2 dimension, right? Because we are looking at sigma z, which is a 2 dimension, 2 by 2 matrix. To calculate 2 by 2, we are saying that I equal to 0 to 2 minus lambda I. This is ket I and bra I. If you are going to take this, then we are going to get a, this is equal to lambda 0 of 0 0 plus lambda 1 of 1 1, ket 1 bra 1, same way ket 0 bra 0. And if you do a multiplication of that, this ket 0 bra 0, what we expect is we are replacing them, right? So let's say if we have lambda 0, lambda 1 is known to us to be plus 1 and minus 1 given. So we have 1 and we have minus 1. Also, we have the vectors given to us as 1 0 and 0. So if we are going to multiply this is nothing but, you can say 1 into anything is same, but at the same time we have 1 0 into 1 0, so 1 1. So this is a matrix which turns out to be identity here in this case. No, not identity, sorry, 1 into 1 plus 0 into 0. So you got 1 into 1 1, and this, so sorry, this is 1 into 1 1, 0 into 0 0, and then we are getting 1 into 1 plus 0. So basically what we are turning out is we are trying to solve this 2 by 1 into 2 row 1 by 2. So essentially we have calculated this based on the number, and we are ending up in 100 minus 1. The calculations here, what we have seen are available. The what you call one is I have got a couple of things I have made already. I have done it on the basis of uh, uh, column row matrix as well as on the basis of uh, what you call manual calculation. We'll work on that, but essentially these are matrix computation, and we have to make sure that we get a value which is this 100 minus 1. So I'm not getting into integrated here at this time because sometimes it confuses and it confuses the whole class. When we have the session on the computation, we'll do that. But essentially, this is turning out to be 1000 plus 00 minus 1. This is one multiplication, this is another multiplication. So if we take these two, and because there is a plus in between, so you have this computation plus a plus in between. So when you do sum of these two, we are getting 100 and minus 1. So 100 minus 1, which is what we started with sigma z. So that is we had done previously. We were given this and we computed the other way around. So you can construct operator from eigenvalues and eigenvectors similar to this, and the references I am giving here. We have the calculations here, and which is what I was trying to point out, that if I go to sigma z calculation, and you can see here we have is QCS 101 S04 sigma z computation we have done. If you have 100 minus 1, and if you have ket 0 as 10, then you do multiplication and addition, and you came out as 10. Same way, if we do with respect to 01, you can see 1 into 0, whatever the numbers there, row, column, row, column, row. So then it turns out as 0, 1 or minus 0, 1, which is Kitman. So essentially, we do have a computation which we did previously, and that is in the session 4. And this is a manual calculation. I have put it in the, we call it as some Jamboard or something, and that is what I have put it. But it is available to you. Okay. Same way, polymetrics. What are polymetrics? We need to remember them, and therefore, I don't know whether it is showing up on the screen for you. No, I don't think it is not showing. So let me do one thing. If it is not showing on the screen, it doesn't mean for you to follow. So let me put it this way. If, uh, let me go back. These sigma z calculation, polymetrics calculation, poly combo of basis changes, these three are put on the Jamboard. And if I click on this, the sharing doesn't occur. So I don't want to break the continuity. Let me summarize and then I'll go back. So what we have covered in the session, which is significant, is of orthonormal vectors. So what is the significance of orthonormal vector? It is simplification of vector rotation. So they call it sometimes even sparse metrics and all that. Basically, what it means is you zero when you do a determinant, you try to zero and try to get maximum zeros, and then you do the minimum computation. It is something similar here. Here we have the Kronecker notation J ij. If I equal to j, then you get some value I naught equal to j, you zero out the whole matrix and use the computation. So our approach is always trying to minimize, because we are doing orthonormal uh, vector basis. It is simple, and the rotation, and we have also limited our rotation of matrix when operating on a vector rotating. It is always a unitary matrix, and therefore neither it is uh, scaled on a higher number or a lower number. If you take a line, then you stretch or squeeze. If you take a space surface, then similarly you do a stretch array of the area. And if you are doing on a 3 dimension, then it is a parallelopoid or something. So it's a volume basically. So if it is a 4 dimension, then we don't know what to call it. So that is where we get into the what do you call uh, induction. That is methods of induction. What you can do in 2, 3 can be done for n. We'll come to tensor later in the next class. At this time, I don't want to stretch too much because consolidating is itself important, and plus we'll have Professor Gokhale also coming next time, and so we will be able to do justice to what we have taken up for tensor. So we have to recollect we did Hermitian matrix, which is adjoint, and then we also said that if you are doing coordinate basis, we are going to do anti-clockwise rotation for positioning the vector using the position vector. And if we are going to do basis change, uh, that is change of the basis itself, basis, not the vector rotation basis, then in that case, that is, uh, we will be doing clockwise rotation for that. So TensorFlow is one which will take it to n dimension, and at this time we will just stop here because tensor is required for us for a n dimension abstraction, both for the quantum operators for the gate based implementation as well as algorithm based applications. So which are the part 2 and 3 of it, part 2 and part 3 of it. So we are almost at the end of part 1, except for one more class where we one more session, sixth session, where we cover the tensor and the operations, tensor operation to complete the task. So before I close, I will just say that there is an assignment available to you. Unfortunately, if I click on this, it doesn't show up. So I have to, if I, example, I calculate sigma calculation, right? Now, I don't see, you can see this. If you cannot see this, then what do I do? Then I go to my, this one and says stop sharing, and then again reshare. If I reshare, uh, share the screen, and this time show the Jamboard, then you can see. So you can see here how, if you have a sigma z, how do we calculate using the sigma z Pauli matrix 100 minus 100 into ket0 and ket1, and this computation is what we do: 1 into 1, 1 into 1 plus 0 into 0. This is the first cell item. Second, 0 into 1 minus 1 into 0, minus 1 into 0 is 0, and 0 into 1 is 0. So at the end of it, we get 1 plus 0 and 0 plus 0 are 1, 0. This is going from Pauli matrix Z to ket notation or column matrix. Same way here. So this is 1. Okay. So you can look at this Jamboard. This is the uh, session 4 sigma z computation. Okay. You have many more there, but this is one of them. So let me take this off, and again I go back. I will have to go back to my before I show you the polymetric stuff. Let me go to share and share the screen and show the polymetric in this case. So you see here the polymetrics. So here you got sigma x, sigma y, sigma z, and identity matrix, and ket0 and ket1 represented. How to memorize Pauli's matrix 2 by 2? That's why you will find that x and y you can remember together with 0 and 1 and minus I. So 1, 1 and minus I. This is diagonally is both 0 here, and this is 1, 1. This is minus I, I. Simple. Same way, z is very much like identity. Identity has got 1, 1, 0, 0. Identity matrix is very simple, diagonally all 1, which is very clear. But the z, sigma z is nothing. Instead of having the second being minus 1, it will be 1, it will be 1 minus 1. 1, 0, 0 minus 1. So remembering polymetrics is like remembering number 1, 2, 3, 4 in arithmetic or ABCD of the algebra. So this is what sigma x, y, z you have to remember, and then always remember that square of any of these is equal to I. So sigma x square, sigma y square, sigma z square equal to 1. And so that's the way it is. And square of all polymetrics is uh, identity matrix, and plus column vectors represent the ket0, ket1, and any alpha 1 alpha 2 alpha n minus 1 for a n basis. That means when you do a superposition, you can have, this is only for one qubit. If you have n qubit, then you are going to get that superposition of n electron spins, and therefore accordingly you have n states, and therefore that needs to be removed. So you can change basis from Z to X or X to Z because they are all isometric, they call it. That means it's a reference, right? Frame of reference. If you do XZ, then XZ is the reference. If you do YZ, then YZ is the reference. If you do XY, then XY is the reference. So you can change the reference according to the way, and accordingly the vectors will change, and accordingly the matrix needs to be rotated. That means what is applicable if you try to use different metrics. Example, if I want to go sigma x basis, then even though I am doing sigma x basis, I'll have to use equivalent of that matrix for the changed basis. Hopefully you are getting it. If not, realize these are only valid for Z basis. If I have to do the same thing, put a sigma x here, then that is, even though we call it sigma Z, for the basis sigma x, I'll have to use this to make it again eigenvector and eigenvalue as plus minus 1. Otherwise, you will not get it. So, of course, there are many eigenvalues. That means if you have an n by n equation, linear equation, you can have number of solutions. But the solution that we are interested in quantum is plus minus. Okay, I'll take out this and again go back to share. Before I share, I will show one more. So here, let me share before I talk so that you are aware what I am talking about. So here I go, I share the screen, I share the Jamboard, and hopefully you can see now. So I've just kept here gamma just because it's a special value. I need to remove this, but I'm keeping it because sometimes you need to show alpha, beta, gamma, delta, and so many, and they are not writable directly, and using a pen to do the work is harder. So what I have done is I've just shown you these are matrices. These are the matrices 0, 1, 1, 0, 0, minus 1, I0. So polymetrics, sigma x, y, z. Z basis, how do you compute? X basis, how do you compute? Y basis, how do you compute? And there is a matrix available in the website here on the wiki page, and which is also giving you that x, y, z, x, z, x, y, z, I. So basically, if you do sigma x, I, sigma y, I, sigma z, sigma. If you do any alternate, like if I multiply sigma x by sigma y, then I am getting minus I z, I sigma z. Same way, if I go corresponding to that, in the transpose area, there is A01 to A10, then that is giving I sigma z. So if you go, that means what? If you multiply sigma y by sigma x, you get this. But if you multiply other way around, sigma x by sigma y, then you get. So they are generally conjugate, or they are negative of opposite of what it is. So here it is like this, I sigma y minus I sigma. So you can look at this matrix and get to know better. I think I will stop here. I am running out of time, and I need to finish this one. So here we are. This is the summary. The only thing I want to add is assignment 050102 has got the problems, and we will discuss that in the either the session or in the office work. And next time we will try to cover the Hilbert space and expansion of Hilbert space and tensor product. We'll talk about multi-qubits, Hilbert space and tensor products, and multi-qubits and tensor product, about tensor product and Hilbert space and problems. So this will be the 6th session. I hope that will be final session. If need, we may add one more session to complete the whole thing. With this, I think I am going to stop the recording, and we are on Yes.